Welcome to qnawire.
For this problem on the topic of sources of magnetic fields, we are given a pair of Helmholtz coils, and we are told that each is wound with N turns and a current of I in the same direction. If we allow the radius to be A, and if we look at the configuration as given in the diagram, we want to calculate various properties of the magnetic field. Now, firstly, we want to find an expression for the magnetic field B at a point on the x-axis, that is a distance x to the right of point P. And this point is actually midway between the coils. Now we know for a single loop that the magnetic field B is equal to mu naught I a squared over 2 into x squared plus a squared to the power 3 over 2. But here we have two loops, each of n turns, and if we measure the field along the x-axis between them, means that x is different for each coil. So for the left coil, this value for x is actually x plus a over 2. And so the magnetic field due to the left coil, BL, we'll call it, is equal to mu naught times n times I a squared divided by 2 into x plus a over 2 all squared plus a squared to the power 3 over 2. Now for the right coil, x here is now x minus a over 2. So the magnetic field looks as follows. So the right coil has magnetic field BR, and this is mu naught n I a squared all over 2 into x minus a over 2 all squared plus a squared, and all of this to the power 3 over 2. So now to find the total field at a distance x from the point between them, we'll call this total magnetic field B, and B is mu naught times n I a squared over 2, which is the common term. So we sum the fields due to the left and the right coil, and we get this into 1 over x plus a over 2 all squared plus a squared to the power 3 over 2, and this plus the field due to the right coil, which is x minus a over 2 all squared plus a squared, and that also to the power 3 over 2. So here we have our expression for magnetic field at a distance x from the point between the two coils P. And that's our first solution. Now for part B, we are asked to graph B versus x for x is equal to 0 to x is equal to a over 2. And then compare this graph for the magnetic field due to the right coil alone. So here we have a diagram, a graph, as required. So firstly, our total graph of B versus x for the total field from between our values for x, and secondly, a graph of the field for the right-hand coil alone. And those are our two required sketches. Now for part C, we are required from part A to obtain an expression for the magnitude of the field at point P. So we've done so for a distance x from point P. Now we wish to calculate the resultant magnetic field at point P. Now we know at point P that x will be equal to 0. And so therefore we can use that expression from part A and find this resultant field B. So we know B is equal to mu naught n I a squared over 2 into 1 over a over 2 all squared plus a squared all to the power 3 over 2. Remember, x is 0 here at p, plus 1 over minus a over 2 all squared plus a squared to the power 3 over 2. And so simplifying this, we get the magnetic field at point B will be mu naught n I a squared all over 5a squared over 4 to the power 3 over 2. And we can simplify this even further, and this becomes 4 over 5 to the power 3 over 2 times mu naught times the number of turns n times the current I over the radius a. And so we have an expression now for our resultant magnetic field at point P. Now for part D, we want to calculate the magnetic field at P if we are given the values for N, I, and A. So we've just calculated the expression, we've just derived the expression rather. Now we can calculate a numerical value. So we know B from above is 4 over 5 to the power 3 over 2 times mu naught n I over a. And if we substitute the given values into this, this becomes 4 over 5 to the power 3 over 2 times the constant mu naught, which you know is 4 pi times 10 to the minus 7 times the number of turns 300 times the current I of 6 amperes divided by the radius A, which is 0.08 meters. Since all our values are in SI units, we get a magnetic field in Tesla to be 0.0202 Teslas. So that's the magnetic field at point P with our given values. Now, in part E, we want to find dB dx and d2b dx squared. So we want to find the first and second derivatives of the magnetic field at point P and show and discuss how the results show that the field is quite uniform around point P. Now, let's take first our expression for the magnetic field at point P and take the first derivative with respect to x. So dV dx is equal to mu naught n times I over a, and this is into minus 3 into x plus a over 2 over x plus a over 2 squared plus a squared to the power 5 over 2 plus minus 3 x minus a over 2 all over x minus a over 2 to the power 2 plus a squared again to the power 5 over 2. And so here we have an expression for dB dx. But now at point P, remember x is equal to 0. So we need to evaluate this at x is equal to 0. So dB dx at x equals to 0. If we substitute x equal to 0 at this point, we get the following. This becomes mu naught n I multiplied by a squared. It's actually a squared divided by 2, not divided by a. And this is all multiplied by minus 3 into a over 2 divided by a over 2 squared plus a squared to the power of 5 over 2 plus minus 3 minus a over 2 over a, or minus a rather, over 2 all squared plus a squared to the power 5 over 2. And if we look at this carefully, we see that this is actually equal to 0. So the terms in brackets cancel out, and we left with dB dx at point P, where x is equal to 0, is itself equal to 0. Now we need to do the same for the second derivative d2b dx squared. So d2b dx squared, we'll first take the first derivative, we'll derive the expression for dB dx once more with respect to x, and then equate that at x is equal to 0. So the second derivative is mu naught n I a squared over 2 into minus 3 over x plus a over 2 squared plus a squared to the power 5 over 2 plus 6 into x plus a over 2 squared times 5 over 2 divided by x plus a over 2 all squared plus a squared to the power 7 over 2 plus minus 3 over x minus a over 2 squared plus a squared to the power 5 over 2 plus the last term, which is 6 into x minus a over 2 all squared to the power 5 over 2 divided by x minus a over 2 all squared plus a squared, again to the power 7 over 2. And so here we have an expression for the second derivative of the magnetic field at point P with respect to x. Now at point P, x is equal to 0. So we need to evaluate this d2b dx squared at x is equal to 0. So all we do is substitute x is equal to 0 into the expression above, and we see that if we substitute x equal to 0 into this long expression, we again are simply left with 0. So d2b dx squared is also equal to 0. Now, since the first and second derivatives are 0, this means that the magnetic field can only be changing very slowly, and so the magnetic field is fairly uniform at point P.